Now that we know the derivative of the inverse trig functions for sine, tangent, and secant, let's talk about integration formulas to reverse that differentiation for at least two of those. Again, these two in red are the two that you're going to be responsible for because that's what we're going to see on the test most often. It turns out that we just really don't see the integral of secant inverse very often. We see these quite often, however, so we definitely need to make sure we have these in our head. So remember, if we have a function y equals the sine inverse of some expression in u, or t, or b, or s, it doesn't matter, some expression in x, I mean, over a constant, and we take the derivative, then we know where we wind up with that. But if we are integrating something that is definitely the derivative of the sine inverse function, then we know its antiderivative is the sine inverse of u over a. So we're going to look for 1 over the square root of a, or a constant squared, minus some expression in x squared. And so when we see that, we're going to be doing u substitution. All right? And so here we can clearly see the derivative of the tangent inverse function as well. So the antiderivative is the tangent inverse of u over a. This may not be quite as intuitive, and I'm not going to take time to develop it. Again, these are two formulas that I would just out and out memorize, and you see these often enough on the exam that you just need to know them. So I'm going to work several examples, and then when you come to class next time, you can work some homework problems and get more comfortable with this. So let's just dive in working some examples. So if we are given a definite or indefinite integral, and we see a square root in the denominator, well, before, if we had seen something like this, 49 minus x squared dx, we would say, okay, well, what's being operated on? We'll call u. This is just for example. And then so du would have to be negative 2x dx. And if we didn't see this x anywhere, then we could not find the antiderivative of that function. We were going to be off by more than a constant. And so we could do it if it were x over that, because then we would only be off by a constant. So when you do this and it looks like you're off by a variable, think of sine inverse, all right? Think of sine inverse, and I might even write it in this way to help you identify a and to help you identify what expression in x, what u would actually be. So it turns out that this is really not a u substitution problem at all. This is kind of straightforward sine inverse. So remember, the antiderivative is the sine inverse of u over a plus c. It's as simple as that. So here's another one, and we might rewrite this again to kind of help us see. We'll pop that 2 out front. So we have 1 over the square root of 3 squared. That helps us identify a. Minus, this would be the quantity 2x squared. All right, so this is definitely a u substitution problem. We would need to show the AP reader we recognize u is 2x. Therefore, du is 2 dx, so we're not even off by a constant because our 2 is in there. So this antiderivative, if we want to do, again, in u substitution, we do the indefinite integral, would be 1 over the square root of the quantity 3 squared minus u squared du. And so the antiderivative of that would be the sine inverse of u over a plus c. Now this is a definite integral, so in our definite integral process, we substitute back into terms of the original variable. For us, u was 2x over 3. We drop our plus c because we only did the indefinite integral to find our antiderivative. And now we're going to do fundamental theorem. So this is the sine inverse of 2/3 minus the sine inverse of 0. All right, and this is not an exact value, so clearly this would be a calculator active problem. If this was like pi or something like that, I might try to evaluate that with my exact values. But we'll go on and work another couple of examples here that have to do with tan inverse. So there's no root in the denominator. Things we're going to look for to see whether it's a trig inverse antiderivative or just a regular u substitution. We don't have a root down here, but we do see that we have an x squared. So if we chose all of that to be u, then du would have an x in it. The derivative of that would be 32x dx. So we can clearly see here there's no x up here anywhere. So we want to start thinking now of tan inverse. All right, and so if that's true, let's pop our constant out front. I always find it easy just to get the constants out of the way. A is 5, and now what was squared to give me 16x squared was 4x. So this is a u substitution problem where u is 4x. du therefore has to be 4 dx. So again, I want to recognize in this context that a was 5. So the antiderivative of this function, I popped my 3 out front. I'm going to have 1 over a, remember that, times the tan inverse of u over a. And there we are, right there, and then plus c. Okay, so there's the antiderivative function. And lastly, we'll do this last example. This one's a little more tricky, but again, you're going to have kind of a mixed bag of integrals in front of you, some of which are going to be straightforward u substitutions like we've always done, and now some of which are going to be tan inverse or sine inverse. And sometimes it's hard to see. Here again, if we chose what's down here to be u, then when we found du, we would have 2x plus 8 dx. And so there's our first clue, since this is just 2 and not 2x plus 8, there's our first clue that this is not a u substitution problem and that we're going to have to try to answer this in a different way. All right, so let's go back and we'll work this one. I want to try to get this, I'm going to pop my 2 out front. I want to try to get this where I have a squared plus some expression in x squared dx. So I can identify a and identify u, but it's not as straightforward as this is right here. This is actually a trinomial here. And so I need a constant a, and I need an expression in x. And so the trick here is to complete the square on the x squared term and the x term, and whatever's left over becomes a squared. Because then you'll have a perfect square trinomial, and you'll have x, plus or minus something quantity squared. So completing the square is to take half of b and square it. So half of b is 4, and that squared is 16. And so I'm going to borrow 16 of these 17 units that are out there of the constant 17. I need 16 of it here. And so this can be rewritten like this. So now I have 1 squared plus the quantity x plus 4 squared. So u is x plus 4. du is simply dx. So I'm going to rewrite this in terms of u and du. And a is 1. I have a 2 popped out front, so that's already there. And so it's 1 over a, which is 1, tangent inverse of u over a, and I'm not going to write the over 1 because we normally don't, and then plus c. And so there it is, right there. There's the antiderivative function. So one quick little video. There's really only 2 formulas that you need to know. Again, make flashcards. Make sure you know them. Come to class next time and we'll do some integral work on the 2 inverse trig functions that we should see on the exam.